Good evening, everyone, and thanks for joining in a bit early. And sorry for 15 minutes delay. And today's session will be taken by Mr. Mujana sir. Let me give a small brief about him. Dr. Manjuna sir is a PhD holder. He's an accomplished researcher, educator with over 21 years of academic experience and 16 years of research expertise in electrochemical energy, storage, and conversion systems. His work centers on the design of advanced battery materials, supercapacitors, solid-state electrolytes, and electrocatalysts for hydrogen generation, with applications spanning electric vehicles and sustainable energy technologies. He has authored 115 peer-reviewed publications, including 38 in Q1 journals, with a H index of 25 and 1800 plus citations, 4 patents, and several front cover featured in leading journals such as ACS Applied Electronic Materials, Energy and Fuels, and Chem. Recognized among the world's top 2% scientists in 2023 by Stanford University, he has also received an ICTSGS Service Award from ACS and ECS Japan 2021 and multiple excellence awards for research and innovation. He is a member of the Royal Society of Chemistry UK, Electrochemical Society USA, and American Chemical Society USA. Dr. Manjunath sir actively contributes to advancing battery technologies, electrochemical modeling, digital twinning for EV systems, became a leading voice in the field of energy materials and electrochemistry. With this, I welcome you, sir, for today's bootcamp.
Thanks, Mike, for the introduction. So, hi everyone. Good evening, and I appreciate everyone joining for this webinar. That too this late evening, and also this is a weekend. Okay. Anyway, sorry for the delay for 15 minutes. Okay. So the topic of today's webinar is the very important topic to understand the battery dynamics, the physical and chemical process of the battery is probing the internal processes of lithium-ion batteries using electrochemical impedance spectroscopy. So in this webinar, in the next one hour, I'll be covering these are the topics that is I'll be introducing to the EIS, why it is important for the understanding lithium-ion battery chemistry, and what is the impedance, and also the AC response, and the frequency domain versus time domain, and also the time constants. And I'll discuss briefly about some of the basics like phase shift and the complex impedance with respect to various circuit and circuit elements. And I'll be discussing about the equivalent circuit modeling for lithium-ion cells, how a battery is being converted to an electronic circuit. And we understand the battery chemistry, the processes by using the two plots, very famous plots called Nyquist and Bode's plot. And we will understand the different frequencies in the Nyquist and Bode's plot. We will be getting the information about various different processes that takes place in lithium-ion batteries, and Warburg impedance, about the diffusion, etc., and the EIS measurement to the concentrations. And just at the end, I'll summarize and the key takeaways of this topic. So actually, it's a very wide topic. In my master battery materials and digital twinning, that master degree course, which is launched by Decibels, and we had this is a very important topic for the digital twinning. And the content that I have covered on this topic is about almost 8 to 6 hours in detail. I'll try to touch all the aspects that I have covered in those recordings in the next 1 hour. We know that the lithium-ion battery consists of various components. For example, this is the representation of the battery, and you can see this is the left-hand side. This is a copper coil, a thin coil coated with the graphite. So the graphite acts as an anode. Of course, the graphite is not just a graphite; it is also filled with some pillars, that is binders, in order to stick to that copper foil. So this will be the anode component, current collector, and as well as active material. And during the formation, after fabricating the battery, we do formation cycle, that is conditioning cycle. During that, there is a formation of very thin film on the surface of the graphite, that is called SEI, solid electrolyte interface. It's actually made up of lithium oxides, lithium carbonates, and very porous film that is formed. And I have discussed in detail in some of the videos in that course about the SEA importance. And then that is in contact with the electrolyte. Electrolyte is basically non-aqueous organic electrolyte made up of ethyl carbonate or methyl carbonate containing the lithium-ion salts like LiPF6 or Li AlCl4, the salts. So then that is being uh, and that this anode part is separated, anode and cathode part are separated by a thin porous membrane that is called separator. It's actually made up of a polymer, polythene or polypropylene, a very thin film have containing a small holes in that. So then again we have an electrolyte component, and then the right side we have copper, cathode compartment. This cathode is consisting of aluminum as a current collector. So aluminum as a current collector, and that is being coated with the cathode active material. For example, if it is an NMC battery, it is being coated with NMC cathode material, and if it is LFP, it is being coated with LFP material. Of course, this cathode material is having the conducting filler, some carbon also being added, super P, and also some binders. So it is having a binder and also the conducting fillers. The conducting fillers is to provide the channels for the electron flow in that electrode material. So then, as I mentioned, during the formation of SCI on the anode, at the same time there is a formation of another film on the cathode surface. So that is called cathode electrolyte interface. That is also porous in nature, that prevents the leakage of transmetal ions. So this is the overall physical, the components that battery has. If you look at this diagram, you can say we have a metals, conducting metals like copper and aluminum. We have a conducting graphite anode, and it is having some polymer and metal oxides and liquid and a polymer. So the chemistry of this is really complex. It's not just made up of one component. Suppose if it is made up of one component, then the chemistry is very simple. Understanding that the mechanism is easy. Since it involves various components starting from organic to inorganic, polymer, metal oxides, conducting, semi-insulating, all those materials. So the battery chemistry is very, very complex. It's not easy to understand. So in order to understand the processes, we use electrochemical impedance spectroscopy. Okay. So we understand in this technique, we understand the how the lithium ion is being so during the charging process, the lithium ion, for example, this is the cathode material containing lithium ion. While charging, it has to move towards the anode, right? To move towards the anode. First, it has to come out from the lattice structure here, the crystal lattice structures. In case of NMP or LMP, they have a different lattice structures. Some are one-dimensional, some are two-dimensional. Of course, they will definitely, the lithium ions will definitely experience the different resistances. So while deintercalating the lithium ion from the cathode material, the resistance experienced by lithium in LFP is not same as that of NMC, right? Because NMC is a 2D material, two-dimensional channel provides, but LFP provides only one channel. So the resistance experienced by lithium is completely different. Okay, so then once it has to come out from that solid matrix, it has to pass this cathode electrolyte interface. It's a porous membrane, and the experience, the resistance offered by thin film is not same as that of that cathode material. So then it has to get into that liquid, so electrolyte. So electrolyte is in liquid medium. So from solid to liquid, when it enters, so there will be a change in the resistance, right? So then that lithium ion has to pass through that solid thin film separator. Again, the resistance will be different. It may not be same. So the rate at which the lithium ion moving is not same. It's not constant. It changes from one stage to another stage. So then again it will enter into the liquid electrolyte. Then it has to pass through that solid electrolyte interface layer, and then it should intercalate graphite. So while lithium is intercalating from cathode to anode while charging, the electrons are made to move from the cathode to anode here. So where the lithium and electron they combine and it becomes metallic lithium, that is called charge transfer process. And the movement of lithium from cathode to anode is mass transfer. So it depends on the process. The resistance experienced by lithium in this process in various stages is represented in the form of some electronic circuit like this. Okay, so this is called Randall circuit, and you can see that the resistance of copper is represented by RCU, and we have the resistance of the anode. This is the resistance of the graphite, and then we have a diffusion resistance that is called Warburg resistance, and the constant phase element. I'll explain this in detail. What is mean by CPE? So then we have the resistance of the solid electrolyte interface, and again it is in parallel with the CPE. Then we have a resistance of the electrolyte, and this is the resistance of the separator. Wherever the solid material is there is always a capacitive behavior because of the accumulation of charges. You can see we have a solid, this is SEI, and this is graphite. But in liquid, we don't have any capacitive behavior because there is no charge accumulation. So, and in separator, because separator is a thin film, we can expect there is a storage of lithium ions at some particular time. So, therefore, we can expect some capacitive behavior also with respect to separator. So, then we have resistance experienced by resistance offered by the cathode electrolyte interface, and then CPE charge. Okay, CPE corresponds to the capacitive behavior of that particular component. So, and this corresponds to the cathode, the resistance of the cathode active material and Warburg resistance, and the capacitive nature of the cathode material, and then we have resistance of aluminum. So all these components that lithium so can be understood by using this electrochemical impedance spectroscopy technique. So this resistance is expressed in this format. So this entire physical system, this is the physical system, can be represented in terms of electronic system. We have simplified it. So then we use a technique and we extract the data, and it is represented by the plot that is called Nyquist plot. So Nyquist plot is actually the impedance, real impedance along x-axis versus negative imaginary impedance along y-axis, and you can see that the semicircles, and then there is a 45-degree line. All these, this plot will give a lot of information. So there is the resistance corresponding to this has different information, and with this one will give information about some of the components, and this part, this region will give the information about the charge transfer, and this one will give the information about the Warburg. So therefore, the EIS is a versatile tool to understand the battery without opening the cell lock. So that is important. So it is actually frequency based. You can see that the fingerprint of the batteries in processes from ion movement to the electrode surface reactions, and without opening the cell. So generally, this is a non-destructive technique. Even if the battery is running, and the battery is being used for a long time, or in the if it is not being used, we can test the EIS and we can understand the battery life from the EIS. So it measures by using this EIS technique, we can understand the internal resistance. So this corresponds to the ohmic classes from electrolyte, contacts, and separators. And it also evaluates the charge transfer process. Charge transfer is actually the electron transfer in the graphite to the lithium, where it undergo reduction reaction. So this is actually basically defines the kinetics of the reaction, and that is mainly based on the Butler-Ulmer kinetics and Tuffle kinetics. I have actually explained in detail about this charge transfer process in some of the videos in that course. So it indicates how the electrode reaction kinetics and the aging effects are okay. And then we can also analyze the double layer capacitance. This is corresponding to the formation of double layer, the accumulation of charges. It reflects the electrode surface area and also the solid electrolyte interface behavior. And EIS can also assess lithium-ion diffusion. This is represented by Warburg impedance. So it reveals actually the solid-state ion transport limitations in electrodes. Obviously, LFP chemistry and NMC chemistry, or if you go to the LTO chemistry or graphite chemistry, this Warburg impedance will be different. So because of the intercalation of lithium ions. Then it will also monitor the SEI formation and also the SEI degradation upon the usage of the battery. It detects the changes in the interface resistance during cycling. And also this technique is used to estimate SOC and SOH. Of course, I'm not covered in detail about this in this seminar. In my course, I have explained in detail. So overall, it tracks the battery performance and life using the impedance signature. Okay. So let us understand some of the basics of EIS. It involves applying a small sinusoidal AC signal. For example, if you apply a small AC voltage, the output will be the AC current. That voltage, AC voltage, that signal perturbs this electrochemical system, that is a battery at equilibrium state. And the system response is measured. If you apply the voltage, and then you can measure the current. And this is done over a wide range of frequencies, typically from millihertz to megahertz, because when you look at the movement of the lithium ion inside the battery, so sometimes it is fast and sometimes it is slow. So therefore, we have to perturb the system at various frequencies in order to extract the information of all the lithium ion behavior in all the stages when it is moving. The resulting data from this electrochemical process reveals that we can understand the charge transfer, that is RCT resistance, double layer CDN, and Warburg ion diffusion and SEI behavior in batteries. So this information is often analyzed, extracted from the frequency domain plots. That is Nyquist plot. So it's the plot which is real versus imaginary impedance. And then we have Bode plot. So it's a magnitude of that impedance versus the phase. And also magnitude of impedance and the phase versus frequency. We can extract two information from this Bode plot. So some of the fundamentals of EIS is that AC voltage is represented by with respect to time, E is equal to T, and E naught is the amplitude of the voltage that we actually apply, and sine omega T. So it is represented in sine and cosine functions in Cartesian coordinate system, and omega is the frequency, okay, at which we are completing that one cycle wave. So then the AC current is measured. This is the input, and the current is the output. Okay. So and there is a difference in the phase phi, that is phi, with respect to the current and voltage, the input and output. In some cases, the current there will not be pi. The phase will be 0. So that will give some information. If there is a plus phi, and it will give some information. If there is a minus phi, then it will give some other information about the battery dynamics inside. This phi, the phase difference, carries the information about the resistance. If the battery is behaving only the resistor, it's acts like a resistor, then there is no change in the phase. Similarly, the capacitance, the current leads by 90 degree. So the phase is plus 90 degree, and the inductance, we have one more component that is minus 90 degree. So overall, that impedance equation, so we know that this is voltage and current. So V is equal to IR. We know that so R is equal to V by I. So the impedance equation Z with respect to the frequency is equal to the input voltage divided by the output current in AC current. Input AC voltage divided by output AC current. So that Z is represented by the real impedance and imaginary impedance. So the Z, the real impedance corresponding to only the resistive behavior of the battery. If there is no capacitive or if there is no inductive behavior in the battery, so then in whatever the resistance you get, it is just the real resistance. If the battery involves the capacitive components or the inductive component, then we have this imaginary component, so Z double prime. So I'll be discussing that in detail. So why do we use AC in EIS system? So we know that DC is used for charge discharge studies in the battery. Of course, DC is also used for battery testing for different applications. So this the limitations of DC technique is it leads to limited polarization and also the large over potential and mixed contribution. Therefore, we use AC current and AC voltage. So because it provides the linear response and no damage to the battery, and very importantly, the frequency. Okay, DC is with respect to only the time domain analysis. We can't extract what is that, the frequency related information, because the battery process, as I mentioned, lithium moves from cathode to anode during charging. It will not flow with the same speed, right? So we have to disturb the system, sometimes fast and sometimes slow. That is not possible with the DC current. So the very important one is to extract the frequency related information. So AC current or AC voltage perturbation is significant. That's why we use this in EIS. So this frequency that we apply, that perturbing the system, the voltage that we vary from plus to minus, it varies from millihertz to kilohertz. So the kilohertz to megahertz, the information, you can extract the electrolyte resistance. Okay. So then if it is lower frequency, 10 to 1001 kilohertz, so it will give information about charge transfer. So then less than 1 hertz means at very low frequency, the diffusion means the intercalation of the lithium ion, the mass transfer in the solution and also in the electrolyte. That information can be extracted at this frequency. Okay. So the various frequency ranges will give the information about the behavior of various components in the battery. So these are the various circuit elements that you can expect in any electrochemical system. Of course, if you design the battery, sometimes the battery is having a resistive component and also the capacitive component, because it is having a solid and liquid electrode interface. So of course, you can expect the accumulation of charges on the surface, that resulting into the capacitive behavior. So then we have an inductive component. Of course, the inductive component is less. Sometimes inductive component is mainly due to the coiled nature of, for example, in cylindrical battery. So the battery is designed in a cylindrical form. The electrodes are being coiled cylindrically. So whenever there is electrons are moving in a circular fashion, it experiences some resistance that is due to inductance. Okay, so that is also possible in this battery. Let us understand the time domain equation, the impedance and the phase corresponding to each component. For example, if the battery is having only a resistive component, just assume that the battery acts as a resistor. So then the time domain equation V is equal to IR. Okay, so V is equal to IR. The phasor notation is equal to this with respect to time, and the impedance that you get is only the real impedance, because the phase change is 0, the phase change, that is pi. It means that E is equal to ET, and the AC current and AC voltage moves with 0 phase difference. So with 0 phase difference, and we get in the Nyquist plot the information corresponding to the resistive behavior is always along the real axis, always along the Z prime. Okay. So then, for example, if the battery is having the capacitive component, So the time domain equation is equal to the current with respect to time is equal to the capacitance into the rate of change of the scan rate voltage dV by dt. So the phasor notation is equal to I is equal to j omega c into V. So where we introduce a j because it's an imaginary component. The impedance corresponding to the capacitor is 1 by j omega c. So 1 by j omega c. It is so inversely proportional to the frequency. So just note down it is inversely proportional to the frequency. Of course, admittance is actually the inverse of impedance. Here, if the capacitive component is there in battery, when you apply the AC voltage, right? So the current leads ahead by voltage of about plus 90 degrees centigrade, plus 90 degree, okay? The phase is about plus 90 in case of capacitor. So the information about the capacitive behavior, capacitive impedance, it comes in the negative imaginary axis. Okay, so this magnitude increases with the frequency, and then we have an inductive component. So this is the time domain equation, and this is the phase notation of that, and you can see that. So this information, these formulas are very important in my EIS. So resistive component R is equal to R, capacitor, that is a real component, and the imaginary component is the capacitor and as well as inductor. So capacitor is 1 by j omega c, and inductor is equal the the inductance corresponding to this component. Zc is 1 by j omega c, and ZL is equal to j omega into L. So you can see here, this is inverse of frequency, and this is directly related to frequency. It is because it is exactly opposite behavior of the inductor. Here the current lags voltage by minus 90 degree, minus 90 degree. Okay, this appears in the positive imaginary axis. So of course it increases with increase in the frequency, directly proportional. Here the capacitor decreases with the increase in the frequency. So this is about the EIS. I'll just the purpose of EIS is characterize the charge transfer, mass transfer, and interfacial phenomena in batteries by applying the small sinusoidal perturbation like voltage, and we measure the resulting response also in AC format. So then the data we get is the impedance Z is equal to Z prime. This is real and this is imaginary, giving both. So this is the resistive component and this is capacitive and inductive component, resistive and reactive information. So this information is plotted in two ways, that is imaginary part, negative imaginary part along y-axis, and positive real part along x-axis. So this plot is considered as a Nyquist plot, and we have this information can also be plotted by taking log z along y-axis and log frequency along x-axis. So that is one information. And in the same graph, we also plot the phase, the pi, the variation of the phase angle with respect to the variation in the frequency. So this is called Bode plot. This is called Bode plot. So let us understand the difference and importance and advantage and disadvantage of these two plots. Like this plot, as I mentioned, it's minus z prime, that is imaginary versus impedance versus the real impedance. So real impedance, this corresponds to the resistive behavior, and this corresponds to the capacitive and inductive behavior of the battery. So each point corresponds to a specific frequency, but the frequency not directly visible here. In the Nyquist plot, the frequency component is not actually represented. So it advantages of Nyquist plot is that visually represents, we can easily understand the resistive and also the capacitive behavior from that graph. And it identifies the semicircles, charge transfer, resistance, and also the time. I'll just show you that Nyquist plot in the next slide, the diffusion. The disadvantage is that the high frequency region is poorly resolved, and low frequency values dominate axis scaling. So no direct, this is actually one of the drawbacks. So we don't get any frequency in the and impedance correlation in this graph. So that's why we have one more plot that is called Bode plot. So it has actually two plots. One is the log of magnitude of the impedance. Here we have a real and imaginary, but here we have log of magnitude of Z, the total impedance versus log of frequency. Okay. Here we have a frequency along x-axis, and this is along y-axis, and this is along x-axis. And also, we also plot the phase change, the pi, negative pi along y-axis, and log f along x-axis. So the advantage of Bode plot is that directly links the frequency. So frequency with Z, that is impedance, magnitude Z, and also the pi. Simultaneously, we can understand the Z and as well as pi. So excellent for visualizing the wide frequency ranges because so it is being converted to log. The f is being converted to log f. So therefore, we can visualize the wide frequency ranges. So it also highlights the time constants and the multiple processes and system behavior transitions. So useful when data scattering occurs. So this is preferred system diagnostic on models fitting. So this is about the difference between Nyquist and Bode plots that we actually plot. The EIS data is being plotted. So let us understand the impedance equation in various elements. As I mentioned, the battery is having the resistive component, the inductive and the capacitive component. If they're alone, how does it look? How does that impedance equation appears? If they're connected in series and parallel, so how the impedance changes? Okay, so for example, if the battery is having only the resistor, assume that the battery is just behaving like a resistor. So the impedance equation Z is equal to, this is Z prime plus Z into Z double prime. Since there are no other components like capacitor and inductor, this imaginary component becomes 0. So then the overall total impedance is equal to resistance. Okay. So impedance is constant across all frequencies. It does not depend on the frequency. Okay. Because if you look at the time domain equation of resistance, there is no frequency dependent term. The Nyquist plot corresponding to this, you can see it. So for example, if the voltage is the input here and the current is the output, AC current, this is the AC voltage and the AC current input. Okay. And it started from 0. You can see that the voltage increases, the current also simultaneously increases. And the voltage increases, current also decreases parallelly. Okay. And there is no delay in the increase and decrease in the voltage and current. The input and output, there is no delay. So therefore, the pi is equal to 0 in this. So pi is equal to 0. So therefore, if you plot the Nyquist graph for this, the battery is having only the resistor. The Nyquist plot is actually the real component Z prime, kilo ohms, versus minus imaginary impedance, negative Z prime. You can see that you will get somewhere the resistance value, the impedance value somewhere here. There is 1 kilo ohm. It is always along the x-axis. So this is the resistance offered by the system. It is about 1 kilo ohm. 1 kilo ohm. Okay. So this clearly indicates that that battery has only resistive component. Of course, in ideation, we never get like this because battery is not just only the resistive component, it has many other components. If any electro system, if you get the Nyquist graph like this, you always understand that it is having only the resistive component. There are no capacitive or inductive components. That is a inference that you can extract from this. A single point along the rear axis, okay, and there are no semicircle arc in this component, and it is independent of the frequency. Okay, so it's independent of frequency, and the voltage and current are in same phase. So phi is equal to 0. The Bode plot corresponding to this, when the circuit is having only the resistor, you can see here the Bode plot is actually the the log of magnitude of the impedance versus the log of frequency. Okay, this is one graph. Another graph is minus pi. Minus pi, this is along y-axis versus frequency. So this is one graph and this is another graph. There are two graphs in Bode plot. The blue color one, the blue color line corresponding to the absolute value of the impedance. You can see here it is always constant. Okay, even though it does not depend on the frequency. You can see that along x-axis, the frequency is changing from log of minus f, changes from, it is not changing. The resistance is not changing. Okay, so this is actually the resistance, overall total resistance. It's not being changed. It is always constant. So it does not depend on the frequency. Okay, and if you look at the pi, okay, the phase change, the phase delay between the voltage and current is zero. Voltage and current is zero, and it is also constant. There is no change. Okay, the magnitude of z, so is actually square root of r square plus imaginary component is zero. So therefore, it is equal to square root of r. So the horizontal line at z is equal to r. So this is the information that you can extract from Bode plot. If any electrochemical system is having only the resistive component. Okay, so in this discussion, what you should extract is that if the phase change is zero, and if the impedance is independent of the frequency, then that that impedance is corresponding to the resistive element in the electrochemical system. So that is the takeaway from this discussion. Next, let us understand if only capacitor is present in the electrochemical system. Okay, so if capacitor only circuit, then the impedance is equal to, as I've discussed, is equal to 1 by j omega c. It is inversely proportional to frequency. And if you take that j to numerator, it will become minus j. The real part is zero. If the electrochemical system is having only the capacitor, the real component is zero. So the imaginary component z double prime is directly proportional to minus 1 by omega into c. Okay, you can see here. So here, this is the voltage input. Actually, there are two information here. So this is the time domain. This is the time domain information, and this is the frequency domain. Of course, in some of the videos in my course, I have discussed what is frequency and what is time domain, what is phasor, and how the sinusoidal waves, all those things in detail. Okay, so here imagine this. Okay, so if the voltage is applied zero, the current always leads by 90 degree. Okay, you can see the current starts here. When the voltage is here at high voltage, the current is zero. Current is here. Okay, so the phase change between the voltage and current, the phase difference is about pi in capacitive behavior. Okay, so when the voltage is less, the current is at maximum, and vice versa. When the electrochemical system is having only the capacitive behavior. So here the current leads by 90 degree in case of capacitor. Okay, so when this input and output, the ratio you will get z, right? So z is the actual ratio of these two. So when you plot that negative, the positive, the real impedance versus the negative of the imaginary impedance, of course, since it is having only the capacitive in nature, we don't get any data on the x-axis, because x-axis corresponding to the resistor. So therefore, we get the impedance along y-axis. You can see that the red color one, which is parallel to that negative imaginary plane, with the electrochemical system is having only the capacitor. So you can see here the impedance is less when the frequency is high, because you can see that it is inversely proportional to Z is inversely proportional to frequency in this case. And frequency is 0 and impedance is high. This is the impedance. This is the impedance. So it's inversely proportional and parallel to that y-axis. Parallel to x-axis is the resistive. Parallel to negative z imaginary is a capacitor. Okay. The straight line along the negative y-axis, the real impedance is 0. That is a takeaway. So impedance decreases with increase in the frequency. Okay. That is about Nyquist plot. Next, let us look at the Bode plot. Okay, Bode plot, as I always explained, already explained, it is the log of absolute value of impedance versus log of f. That is a blue colored one. You can see that it is inversely proportional to the frequency. If frequency increases, it decreases and frequency increases. You can see that increase in the frequency, it is about 6 kilo ohm and it decreases to 0 when the frequency is about log of f is equal to 5. So this decreases. This clearly indicates if any electrochemical system, if you record Nyquist Bode plot, if it appears like this, then it is clearly indicates that it is a capacity. It has only capacitor. And you can see that the phase change is about it's actually -5. So -5. So it is about 90 degree. Okay. The phase voltage is delayed. So the voltage is delayed by 90 -90. That's why it is constant. Okay. So the phase change is constant in capacitive in the capacitor. So for a pure capacitor in a Bode magnitude Z, Z is equal to, if you take you will get 1 by omega C. Omega is equal to 2 pi f. Then if you take log of Z, you will get minus log of log 10 2 pi into C minus log of f. So this is along the x-axis and this log of z along y-axis and this is along x-axis. And you get this is as a intercept. From that you can extract the capacitance from the intercept. So straight line with slope -1. So the green component is actually the phase 1. The voltage across a pure capacitor always lags current by 90 degree. So the phase stays constant -90 degree across all frequencies. So that is about Bode plot. Similarly, if inductor is there, inductor is exactly the inverse of that. So it also comes under imaginary part. So if the inductor is only present in the system, if the inductor is only present in the electrochemical system, then the real component is 0. So only the imaginary part that is directly proportional to the frequency and inductance. Okay. So you can see in this time and frequency domain plots. Here the red one is the voltage. When the voltage is here and the current is low. But in case of capacitor, it is exactly opposite. It is delayed by pi. Or you can see the voltage is led by pi angle. There is a phase difference. For resistance, pi is equal to 0. For capacitor, pi is equal to 90. For inductor, the phase is equal to -90. Okay, this is the difference. And because of that, the Nyquist plot, you get the impedance value along the positive axis of the Nyquist plot. So here this portion is the frequency is 0 and the frequency is high. You can see here when the frequency increases, so Z also increases. It's directly proportional. So here the impedance increases. Impedance increases in this direction with increase in the frequency. Okay. So since Z double prime is positive, so minus into minus plus, you will get minus and minus. That's why it increases. The plot is a vertical straight line along the imaginary axis, but the projected downward into the negative region. So anyway, minus into minus will become plus. Starts at an angle at the origin at low frequency. At low frequency and extends downward as frequency increases. Since constant at plus 90, the phase, so the phase is plus 90, it means that the voltage leads current by 90 here. You can understand from that. So, and the Bode plot, if electrochemical system is having only pure inductor, you can see this log of Z versus log of F. It is increases with increase in the frequency. You can see that it increases. Initially, it will be 0. The log, no, whatever that the log Z, the impedance is 0. With increase in the frequency, it increases. And the phase is almost constant, minus into minus, it will be plus. Okay. So this means that voltage leads by current for about 90 degree. Okay, or you can say the current lags 90 degree, minus 90 degree with respect to the voltage. So this is how we get Bode plot with respect to the pure inductor. So the overall the impedance equation is absolute value of impedance is equal to omega into L. We know that omega is 2 pi f into L, and if you take log Z means log of 2 pi L, and this is actually positive slope you get. So this is y, and this is x, and this is the intercept slope. Okay, you can extract impedance, inductance from this graph. Regarding the phase component, for a pure inductor, the voltage leads current by 90 degree, and the phase remains constant at 90 degree for all the frequencies. Okay, so that is about the simple circuit elements if an electrochemical system has. Okay, if there are only one. Of course, in ideal cases, we cannot expect, there are ideal cases. In the real electrochemical system, it may be the combination of all three, or it may be the combination of resistor and also the capacitor. Sometimes they may be in parallel, or sometimes they may be in series, right? In that cases, the impedance experienced by that system will be different. Let us understand the EIS response for the electrochemical system in which R1 and C1 are connected in series. So far we have discussed if the electrochemical system is having only one element. If it is only resistor, how does that impedance be changes? Or if there is only the inductor, or if there is a capacitor alone, how does the impedance changes? Now in this case, you can see this is the electrochemical system. In this, we have two elements, the resistor and as well as the capacitor. Both the components, they are in series. So in that case, the Nyquist plot, you can see that the Nyquist plot minus Z double prime versus Z, you will get a parallel line, but not along the axis. It is somewhere after some 1 kilo ohm. It means that it has both the components. The Z, this is also Z. So this corresponds to the resistor, and this corresponds to the capacitor. Okay, so this is along the real axis, and this is along the imaginary axis. So you can see that it decreases with increase into the impedance corresponding to the capacitor decreases with increase in the frequency, because it's inversely proportional. This is how you get the Nyquist plot. So the impedance equation is Z is equal to ZR plus ZC. Okay, ZR is R1, ZC is because they are in series, ZR plus ZC, the total impedance 1 by J omega into C1. So the real part is R1 along it is fixed, and the imaginary part is Z double prime, that corresponds to the capacitive impedance, that is minus 1 by omega C1. The vertical straight line at Z prime, so this is equal to R1, and it extends upward into positive minus Z double prime region as frequency decreases. Here this is a high frequency, omega is equal to infinity, here omega is equal to 0. High frequency point means here R1 is equal to 0. The capacitor is a short circuit. Means if you apply the high frequency, then this acts like a short circuit. So then you will have only the resistor. So there won't be a capacitor. Okay, so hence the electron flow, the resistance experienced by electron flow is only due to R1. So that's why it is called R1. Up to here it is R1. At low frequency, the point moves upward. So at low frequency, if you move towards low frequency, the point moves towards upward. Then it has R1. Then it is an open circuit. Okay, that is about when R and C are connected in series. Let us understand the Bode plot. So I have explained about Nyquist in previous slide, and now it is a Bode plot when R and C are connected in series. When resistor and the capacitor, when they're connected in series. Okay, you can see here log of absolute value of Z versus log of frequency. You can see here the impedance decreases when the frequency is being increased. Okay, so at higher frequency it remains constant. So this decrease is due to the capacitive behavior, and the impedance remains constant in this zone because it is independent of the frequency. This is because of the resistive behavior. So therefore, the resistance up to here corresponding to the resistor up to R1, and the resistance corresponding to this, this is corresponding to resistor, and this corresponds to capacitor. So this is how we extract impedance impedance from the Bode plot. In Bode plot, the impedance is extracted only from the y-axis, that is log of Z. But in Nyquist plot, we extract impedance from both y-axis and as well as z-axis, because one is the real impedance and the other one is imaginary impedance. So the impedance equation again, and the phase equation, the theta, and at low frequency means at low frequency here the capacitor dominates. Okay, at low frequency, so the main resistance, the impedance is due to capacitor. Okay, so theta is equal to minus 90, voltage lags. Okay, so at high frequency the resistor dominates. So at high frequency it acts like a short, the capacitor acts like a circuit. Then the impedance is only due to the impedance is only due to the resistor, because at higher frequency the capacitor acts like a short circuit. Okay, so means it will not offer any resistance, it acts like a short circuit, so the electron can easily move. So at f of c, that is critical frequency. Here, this is the critical frequency where it changes from capacitive to resistive nature. So where both the reactance of capacitor due to capacitor and resistors are equal. So that is called critical frequency. So at minus 45 degree. So at minus 45 degree, there is equal contribution of R and C. Okay, and you can also see that the phase change for this, the angle at low frequency, it is minus 90 degree, minus 90 degree. It is because of the capacitive behavior. Minus 90 degree means it is capacitive. Then it becomes 0 for resistors. 0 phase change, it is the resistor, and minus 90 corresponding to capacitor. Suppose if those elements are in parallel like this, okay, if the capacitor and the resistors, if they are in parallel like the C1 and R1, how does the Nyquist and Bode plot changes? Okay, so the impedance equation, if they are in parallel, is equal to 1 by 1 over 1 by R1 plus this corresponding to resistor, and this corresponds to capacitor. So when you rearrange that equation, if they are in parallel, we take 1 by R, 1 by impedance. Okay, so then when we rearrange this equation, we get the impedance equation for the system containing resistor and capacitor in their parallel. So this is R1 divided by 1 plus j omega R1 series. The Nyquist plot corresponding to this system, when capacitor and resistor, when they are in parallel, you will get a semicircle. So this is the imaginary component and this is the real component. The real part, if you extract from this equation, the real part is equal to this one, and the imaginary component has this one. That is okay. The semicircle in the first quadrant, you can see the semicircle in the first quadrant at higher frequencies. Okay, so at higher frequencies means here the omega is equal to higher and this is 0. So in Nyquist plot, near origin the frequency is high. When it is moving away from that, it will be 0. It will be less. The frequency decreases if it is moving away from this origin portion. At higher frequency, the capacitive reactant is 0. So because when you apply at high frequency means, so this acts like a short circuit. Okay, this acts like a short circuit. So there will not be any capacitor. Then the electron can easily move. Electron can easily move this, and it will not experience any resistance because there is a path for the electron to move in this direction. So electrons start moving in this direction. So therefore the impedance is 0. Impedance is 0. So electron can easily move. There is no resistance at high frequencies. At low frequencies, if you move away from this origin towards x-axis and towards y-axis, so then that capacitive behavior, the capacitive reactance and resistive reactance contributes. So the capacitive reactance, it increases with infinity. The impedance is equal to R1. So the current flows only through the resistor, because at very high resistance, at very high frequency, the capacitive the impedance, because of that short circuit, then the electron flow through that. At low frequency, the impedance is equal to R1. Current flows only through the short circuit, because at low frequencies, then the resistance of this will be infinity. Okay, so at low frequencies, so therefore current has to pass through only the resistor. So it has to pass through only in this path. So therefore the impedance is equal to corresponding to R1. The impedance corresponding to R1. In between the high and low frequencies, intermediate frequencies, the current splits between R and C. That's why we get semicircle. Okay, so it is moving. It has both real and imaginary component. So it is because of both R1 and C1 contributes. Okay, so at this is called mid frequency f of C, where both contributes equally. Okay, both resistor and capacitor contributes equally. This is the information that you can extract from Nyquist plot. Let us understand the time constant. So this is another parameter that is very important in EIS. In parallel RC circuit, it's a measure of how quickly the system responds to the change in voltage. Okay, in EIS, when a resistors R1 and a capacitor C1 are connected in parallel, the time constant is given by omega. Omega is actually 1 by tau. So 1 by tau is R1 C1. Or you can say tau is equal to R1 C1. In the parallel circuit, it is at mid frequency. When R1 in ohm, often it represents charge transfer resistance in batteries. C1, it is double layer capacitance in batteries, and tau in seconds. It tells us how long it takes the capacitor to charge or discharge significantly through the resistors in parallel path. So that is the information that we can extract. So the physical meaning in battery is a smaller tau. The time constant means the fast electrochemical process. It's actually very important. Quick charge transfer response. Large tau means sluggish interfacial kinetics, and broad semicircle in Nyquist plot. So that is information. So this RC pair often represents electrode-electrolyte interface behavior. So this is about the time constant information. So next, we can also expect some other series like where R0 is in series with R1, C1. I'll just briefly explain the other components. You can see here, there are two resistive component and one capacitive component. So where R0 is in series with the RC pair. Okay, so in such system, okay, the impedance equation is equal to R0. Since it is in series, we add this, and this is RC parallel that we have discussed earlier. Okay, so this is the real component and Z component expression for that. The Nyquist plot corresponding to this circuit when the electrochemical system where R0 that is in series with the RC pair which are in parallel. The semicircle is shifted rightward by R0. You can see the semicircle is shifted by R0 at high frequency, means at this zone at high frequency, the capacitive the impedance due to capacitor is 0 because it leads to short circuit. Okay, so then the electron can easily move through. It has to move through only the R0, and then since it is an open circuit at high frequency, electron move in this path. So electron move in this path, and it experiences only the resistance R0. So this is R0. Okay, the impedance is only due to R0. Okay, then at low frequencies. So at low frequency, this will block. Okay, electron will not move because the resistance will be infinity at low frequency. Okay, so therefore the electron has to move through R0 and also the R1. So therefore the impedance is in this system at low frequency is the sum of R0 and R1. Okay, so the horizontal diameter of the semicircle is R1. This is R1 and this is R0. The center of the circle, okay, between R0 and R0 plus R1, R0 and R0 plus R1. Okay, so that is about the Nyquist plot when R0 is in connect with RC pair which are in parallel. The Bode plot corresponding to this log of Z versus log of frequency at low and high frequencies. At this is actually low frequency here, low frequency and high frequency. Okay, at low and high frequency, let us look at the impedance. The capacitor is either sleep. At low frequency, it acts like a infinity. At high frequency, it acts like a short circuit. It's open and it is permanently closed, the capacitor. Okay, at low frequency, the capacitor is closed. Electron cannot move. At high frequency, it is an open short circuit. Electron can easily move. So therefore, you can see that there is no change in the impedance by varying the frequency. It is almost constant because when there is no change in the impedance with respect to frequency, means it is due to the resistor. It is due to only the resistive component. So this one R0 plus R1 and this one, it is due to only the resistive component. So only in the middle range does the capacitor compete with R1. So there is a tug of war between the resistive and capacitive parts, makes the voltage lag. Okay, you can also see the pi is 0, the phase angle is 0. So here and here, only in between these two, there is a change in the pi and also there is a decrease in the impedance. Okay, so just so this overall comparison. When the frequency is 0, it is open. The total impedance is R0 plus R1, and the phase is 0 because it is due to only the resistance. And if the frequency is infinity, then it acts as a short circuit. So then the total impedance is due to only the R0, and the phase angle, the phase change is 0. So only between high frequency and low frequency, the both capacitor and resistor contributes. At very low frequency and very high frequency, only the resistive components contributes to the impedance. Okay, so if you look at the overall now this the battery, the Nyquist plot is for this entire system, which is consisting of all these elements, like we have discussed about the impedance with respect to the resistor and capacitor and various aspects. And the information that we can extract from the Nyquist plot, the real versus imaginary, this is high frequency. This portion is high frequency. If you move away from, the frequency decreases, either along x-axis and y-axis. At high frequency, it is due to the resistance is due to the reactance of metallic structure or the resistance of the electrochemical material. Next, that is R. So then we have the inductive component is also coming up. It is coming down. So this is Z. Okay, this corresponds to the inductance. Then we have a semicircle, the first semicircle corresponding to the charge, the capacitive and the resistive behavior of solid electrolyte interface. Okay, so that is they are in parallel each other, CPE and RCT. Then in the middle frequency, it is because of charge transfer RCT. Then we have, if you move at very low frequency, there is a line, 45-degree line with respect to x-axis at very low frequency that is corresponding to Warburg resistance, that is diffusion. Okay. So let us understand that Warburg and CPE, okay, in the real system. So that real electrochemical system, if you consider, okay, so this is an electrode and we have a bulk solution and this is the interface, right? This is the interface near to that electrode, and the ions has to move from the bulk solution and it has to diffuse through this, and there is a formation of electrical double layer, and then it should enter into the electrode. Okay, so the resistance corresponding to this double layer and this one, this is actually RCT, the charge transfer and double layer, corresponding to this region of the battery. And the lithium ion has to move through that electrolyte. It has to overcome that electrostatic forces in the electrolyte. That corresponds to Z Warburg. And this is solution resistance. So this is at high frequency, low frequency, and this is middle frequency. And this electrochemical system, the process is represented by some electronic circuit that is called Randall's equivalent circuit. Okay, so the Randall's equivalent circuit is an electrical analog of an electrochemical system. It translates the physical processes at the electrode and electrolyte interface in resistors, capacitors, and diffusion elements. So it helps to extract kinetic parameters such as charge transfer resistance, double layer capacitance, and diffusion resistance. So it provides the bridge between the electrochemistry and circuit theory, allowing us to interpret battery processes from EIS spectra. So next we have one more component that is called constant phase element. So actually the capacitor is an ideal case. Okay. In a real electrochemical systems like batteries, the electrode and the electrolyte rarely behaves like a perfect capacitor. It is because of the surface roughness, the porosity, non-uniform current distribution, and distribution of relaxation times, and also there are some side reactions. This leads to deviation from ideal behavior, which is modeled as constant phase element. So CP is actually the real capacitor. Okay. So the real ideal capacitor is exactly should get a semicircle with okay, the radius but in the real battery there is a depressed circle. So there is a depressed circle you will get. Always we get a depressed circle in the Nyquist part because the capacitor that is active in the battery, it's not ideal because of all these practical issues. So the Nyquist plot in CPE. Okay, this is if it is a real capacitor, we get we get like this parallel to this minus redox that we have discussed. We always get slightly tilted line. Okay, this is impedance. So this is represented is because of non-ideal behavior of the capacitor that is represented by CPE. If the resistor and capacitor if they are in series, we get Nyquist plot like this. Okay, so this is the impedance equation for CPE. If n is equal to 0, it's ideal capacitor. Since there is a tilting in the, it is deviating from ideal behavior. Even there is a tilting in the angle that the line which is parallel to the imaginary impedance. Okay, if R is in series with this parallel circuit, then we get Nyquist plot like this. This is corresponding to RU, and the semicircle corresponding to this. And you can see that we are not getting the perfect semicircle. There is a depressed semicircle. Okay, depressed semicircle by an angle theta. So that value is equal to, it is about 0.1, about 10% depressed. We can say that 10% depressed. This is because of 10% deviation from ideal to ideal behavior of the capacitor. Okay. Now, if n is equal to 1, this is the ideal capacitor. This is ideal. And okay, so it is exactly parallel to that y-axis. If it is if n is equal to 0.9, it is tilted by 9 degree. It is tilted by 9 degree. So then this is the equation corresponding to that. So the impedance is equal to 1 by y0 into j omega into the power of 0.9. So these are all non-ideal. So that is called constant phase element. So then if it is 45 degree, okay, if the line is coming at 45 degree, this is corresponding to the diffusion, Warburg diffusion, that I'll be discussing the last component of this. The physical meaning of CP is that if n is equal to 1, the CP behaves like a ideal capacitor. Okay, CP behaves like ideal capacitor. If n is equal to 0, then CP behaves like a pure resistor. Pure resistor. If it is non-ideal, if n is equal to 0.5, it behaves like a Warburg element. So there is 0 for between, if n is between 0 and 1, so it is distributed imperfect capacitance. It's often it's due to, as I mentioned, surface roughness, porous electrode, and various other practical issues. So this is a takeaway from this discussion. If n is equal to 1, it's parallel. If n is equal to 1, theta is 0 degree. It acts like a resistor. Sorry, this is actually, if n is equal to 1, it acts like a capacitor. And if n is equal to 0, okay, so theta is equal to, this is actually 90 degree. Theta is equal to 0 degree. Okay, it acts like a resistor. If n is equal to 0.5, then theta will be around 45 degree. It acts like a diffusion. So the CPE represents non-ideal capacitor behavior in lithium-ion batteries arising from electrode surface roughness, porosity, interfacial homogeneity, revealing the insights into SEA formation and charge storage mechanism. So this can be understood from the CPE. It helps to evaluate the battery performance and degradation, where deviations from ideal capacitance indicate poor surface resistance. Okay, so let me just, I think I'm just running short of time. It's almost 7. Let me discuss briefly about the Warburg. This is the last component. So Warburg impedance is a complex circuit element that represents the mass transfer of electroactive species into the electrode surface, and it typically appears as 45 degree in the low frequency region. This component. Okay, so this is CPA. Okay, this corresponds to Warburg. It always represents the concentration given impedance, the mass transfer, because the lithium ion has to move in that electrolyte, experiencing the various resistances. It has to overcome a lot of electrostatic force of attractions and repulsion. So that is called diffusion. It arises when the ions must move by diffusion in response to the concentration gradient. There is a difference in the concentration and it has to overcome that. So therefore, it has to be measured at very low frequencies. So it's a frequency dependent, typically showing the 45 degree line in the Nyquist plot. So analyzing the Warburg response provides crucial information in ion transport kinetics, whether the transport is fast or sluggish. Okay. So it appears when the rate of lithium ion diffusion is slower than the charge transfer, especially at low frequencies. So it dominant at low frequencies. The impedance is directly proportional to omega to the power of minus of. So let me just, the mathematical representation of the Warburg is equal to sigma into 1 minus j, this is the imaginary component, into omega to the power of negative, that is minus half. So it depends on the diffusion coefficient. So this information is used to estimate lithium-ion diffusion, and it is sensitive to particle size, porosity, and age. Okay. And the Warburg, actually, we have actually three types. One is a semi-infinite Warburg. It assumes unlimited diffusion length. So valid at moderate time scales. It is actually when we get a straight line at 45 degree in the lower frequency region. So typically it is for thick electrodes. This is the impedance equation corresponding to that. And the second type is the finite length Warburg. It's actually the open boundary. So diffusion layer has the finite thickness, no blocking at the boundary. So the lithium ion has to, there is no blocking there. So for this, if that kind of structures are there, the finite thickness with no blocking boundary, then that 45 degree line, instead of coming like this is a 45 degree line, it will form vertical line parallel to the imaginary axis. It acts like a perfect capacitor. So this acts like a perfect represent the capacity lithium ion accumulation. So this is common in porous LIB electrodes. And third type is the finite length Warburg short boundary. The boundary is short. So this is this represents the blocking, okay, ion blocking. So this lithium ion concentration is fixed at a boundary. In this case, that line at lower frequency will be parallel, okay, to the x-axis. So generally we get this. If you're getting that line at lower frequency parallel to y-axis, then it is because of finite length Warburg. If it is, that is open boundary, WO, and if it is short boundary, we get that line parallel to x-axis. So overall, the three types of Warburg are semi-infinite. I have actually in that course, I've spent almost one and a half hour to just explain about this Warburg. So if you take that course, you can explore more in detail. Covering this in detail is beyond the scope of this webinar. Okay, semi-infinite, briefly you can understand that it is early stage diffusion. Finite open means lithium-ion storage with the particles. Finite short means diffusion is blocking and it saturates. The shape of the low frequency tiles, whether it is 45 degree or parallel to y-axis or parallel to x-axis, reveals whether the lithium-ion diffusion is unlimited, stored, or blocked. So this is the information that you can extract from that Warburg. So with this, I'm just concluding my webinar, this bootcamp discussion. So in this today's discussion, we have understood that EIS is a non-destructive technique to analyze electrochemical process in lithium-ion batteries. And small AC perturbation enables separation of real Z prime and imaginary Z double prime impedance components. And battery processes can be effectively represented using the equivalent circuits like R, C, and L, sometimes in parallel series. So the frequency domain analysis distinguishes the ohmic, that is solution resistance, RS, and RCT, and diffusion, the Warburg, etc. Nyquist and Bode plots provide the complementary visualization of the impedance behavior. Responses of ideal R, C, and RC networks from the basis for a real battery interpretation. So that we have also understood the time constant RC reflect the kinetics of electrochemical reactions, and under circuit models key interfacial and kinetic processes in electrochemical systems. And also we have discussed the constant phase elements account for non-ideal behavior of the battery, and Warburg impedance represents the lithium-ion diffusion in electrodes, the nature of the diffusion. And so overall, EIS is essential for LIB material evaluation, aging analysis, and also SOH diagnostics. So with this, I just conclude my discussion. Thanks to all who all joined this late evening and stayed back from 5:30 to almost 7. Thanks for your patience, and also um, uh, I open now. So the session is open for the questions.